Hi guys, today I wanted to talk about nuclear fission, nuclear fusion, as well as nuclear reactors. I think that this will be a good video for you to watch before you do your nuclear energy debate, and also before you kind of get started on your nuclear energy project. So I first want to start out with nuclear fusion. If you were looking at the PowerPoint slides that I posted on the blog with nuclear energy, I think I posted it as a PowerPoint and a PDF. I am going to start looking at the slide that first says nuclear fission. Not positive what slide that is. It's slide number 15. So if you want to look at slide number 15, that's where I'm going to start off at. And again, we're just starting off with nuclear fission. So nuclear fission happens when a really large, unstable isotope changes into two smaller isotopes of two totally different elements. So kind of think about those decay reactions that we've been doing, where we have, like, in an alpha decay, we have an unstable isotope, and it breaks down into a helium nucleus, and then it's also going to break down into a totally different element. So it's the same idea. Now, in a fission reaction, you have to have a nucleus that has a mass larger than 230. So think about all of our elements on the periodic table and their masses. And we have to have a mass that is greater than 230 in the nucleus before we can have some type of nuclear fission reaction. So that's also a really important piece that you understand. The mass has to be really, really big. Now, oftentimes nuclear fission reactions are really, really slow, and they are very spontaneous. For example, uranium is a really common fission reaction, but it takes a really long amount of time for uranium to spontaneously have this fission reaction on its own. Now, we have done something where we can induce a nuclear fission reaction, and that's where nuclear power plants come into play. By us inducing a nuclear fission reaction, we can take a piece of uranium, which uranium will decay over time, and it's just that it takes so long that we need to have that certain energy now that we can use for something else, like generating electricity. So humans have created a method of something called bombardment, which just means that we're going to take a piece of uranium and we're going to hit it with a neutron. So we are going to take a piece of uranium and we are going to bombard that uranium with one single little neutron. When this uranium absorbs that neutron, think about already that uranium has a mass greater than 230. So because it already has a really large mass and it adds another neutron, what do you think happens to the stability of that nucleus if it gains something even more than what it already has? It's going to become even more unstable. So because it becomes even more unstable, it's going to have to start breaking down at a lot faster rate. So we can induce nuclear fission, and that's exactly what we do for our purposes. So that way we can generate electricity, and we hope that it could be a more efficient method than like clean coal, giggles and chuckles. With nuclear fission, again, I just want you to understand, it is where we have some type of really heavy, unstable isotope, a really unstable element with a mass that's greater than 230. We will hit that nucleus or hit that element with one little single neutron. Guys, also, I want to give you the symbol for a neutron because we've been talking about alpha particles and beta particles and gamma particles. And you know that an alpha particle is just that. It's the helium isotope. So we have the 4, the 2, the helium. You know that a beta particle is the electron. So it contributes 0 to the mass. We have a -1 here, and that just represents an electron. a neutron we're going to symbolize with an N, and it's going to contribute 1 to the mass, which makes sense because neutrons do contribute to the mass. But then it's going to contribute 0 to the number of protons, which makes sense because a neutron's not a proton. So that's how we symbolize a neutron, just little FYI here, so that way we can think about doing these bombardment reactions when you come back on Monday. So again, nuclear fission, we have a very heavy, unstable isotope that has a mass greater than 230. We bombard it with a neutron, which means then that really heavy, unstable isotope is going to absorb this neutron into the nucleus. Now it already has this unstable mass, so now that I've given it an extra neutron to incorporate into that nucleus, into that mass, it's just like, it's too much. It's like doing this balancing act. It's like carrying all of this stuff and then piling on one more thing where you lose your balance and everything just falls apart. Same kind of concept. So, absorbs this neutron into the nucleus. It can't handle it, so it has to start breaking down faster. Once this starts breaking down, that one little tiny neutron hits that piece of uranium, becomes really, really, really unstable, and then it's going to split into 2 different things. So fission just means like the splitting. So fission, we are taking a really large, unstable isotope and splitting it into 2 smaller, maybe more stable isotopes. Now, in nuclear fission, we can create something called a chain reaction. And a chain reaction is where that one unstable isotope that's bombarded by a neutron breaks down into 2 smaller isotopes, and then also more neutrons are created through that process. So because I have more neutrons and I have also other available sources of uranium, those neutrons can hit new uranium isotopes, create more stabler isotopes or smaller pieces, which create more neutrons. Those neutrons can be absorbed by other uranium atoms or isotopes, and then those can break down or split off into 2 completely new isotopes. So it's like all of these neutrons can continue to be absorbed by a new piece of uranium, and the reaction can keep going over and over and over and over and over again, as long as there's enough mass of uranium to continue or to keep it going. Now, there's a certain vocab word or a few vocab words that I want you to know. There is something in a nuclear fission reaction called the critical mass. A critical mass means that there must be enough mass in a reaction, or there must be enough fission type mass or a fissionable mass for a reaction to continue to go on. So critical mass just means there's a minimum amount of fissionable material that will allow a chain reaction to continue to go. So if you don't have enough uranium to keep a fission reaction going, then that's something that we would call subcritical mass. So critical mass is the amount of mass that we need to sustain a chain reaction. Subcritical mass, subcritical, subcritical. Subcritical mass is the mass of fission material that doesn't have enough to sustain a chain reaction. So subcritical means I don't have enough mass to keep a chain reaction going. Critical mass means that there's the minimum amount that I have. I have enough. I don't have a lot, but I have enough to keep this chain reaction moving. There is one more type of mass, and that's called supercritical mass. Now, supercritical mass is where there's so much mass that is possible to keep this chain reaction going that there's actually too much where this rate of fission reaction can start increasing. So I could get more energy than what I'm even expecting, and that can be a little scarier. That could be very dangerous in terms of a nuclear reactor. So there's Critical mass, which just means it's the minimum amount of mass to keep a chain reaction going. Subcritical means that there's not enough mass and that chain reaction will eventually stop or die out. Supercritical means there's so much mass that we have, and it could possibly increase the rate of the fission reaction, which could create so much energy that could be possibly dangerous in a nuclear reactor. So that's nuclear fission pretty much in a little nutshell. But I want to talk about nuclear reactors now. And I gave you this handout on Friday that I want you to kind of follow along with me while we talk about this, while we talk about how a nuclear power plant works, okay? First of all, I want you to find where the reactor vessel is, and it says it right here. So the reactor vessel is just right here where the fuel rods are located. So find that reactor vessel. Now, in the reactor vessel, there are fuel rods, and those fuel rods contain that unstable, very heavy isotope. So for example, like uranium would be located in those fuel rods. So what happens in this reactor vessel is that you have a bunch of water that's moving around inside this reactor vessel. Inside the fuel rods, there is a nuclear fission reaction happening. So neutrons are bombarding the pieces of uranium, and then those are breaking down into smaller isotopes. The neutrons that are created from that reaction hit another piece of uranium. They split off, make two totally different elements, but they also make new neutrons. Those neutrons hit more uranium isotopes, so it's just a continuing chain reaction here. But in these fuel rods, all of those nuclear fission reactions are happening, so it's creating a lot of energy inside of those fuel rods. That energy is transferred into the water that's moving around those fuel rods, okay? So that energy, again, that's made in those fuel rods by a nuclear fission reaction is transferred into the water that's moving around the fuel rods in that reactor vessel. Once that water has enough energy, it can move over to where I see, if you follow along here, the water is moving around these fuel rods, has enough that it can start moving to where this pressurizer is, and then it can start moving into a steam generator. So the reason that the water is pressurized is because we don't want that water to boil. If the water starts boiling, then that can cause some type of nuclear meltdown. So we want the water to remain in the liquid state. And if we keep it at a high pressure, then we don't have to worry so much about it boiling. So we can really maintain or control the temperature of that water. So that's why it's pressurized. So let's go back. We have these fuel rods, and they're creating these nuclear fission reactions inside of them. So it's creating tons of energy. Just know that a nuclear fission reaction, same thing as a nuclear fusion reaction, they will always be producing a ton of energy. So nuclear reactions, fission or fusion, tons and tons and tons of energy. So nuclear fission reactions happening in the fuel rods, lots of energy being released. The water absorbs this amount of energy that's being released by these fuel rods. It moves while it's maintaining this pressurized water, so it continues to stay pressurized so it doesn't boil. So we're really maintaining the temperature, keeping it in a liquid state. Moves over into something called a steam generator. Once it gets into the steam generator, that's where that liquid water is going to turn into a gas. Once that liquid turns into a gas, it can start to move these gas molecules because they move a lot faster than liquid molecules do. It's going to start to move something as you move across. So you're in the steam generator, move through the steam line, and you see something called a turbine. All of these really high-powered steam vapor are going to move this turbine. This turbine then starts to make a generator work, which then produces electricity to power our homes. So steam is making the blades of this turbine move faster and faster. So it's creating this turbine to move.